In our last lecture, we talked about how to find the free response of single degree of freedom systems. Here we'll extend that to multiple degree of freedom systems, such as this two-mass system that you see right here. Two masses connected by three springs. I'm assuming that in your previous vibration class you learned how to use Newton's laws or the Lagrange equations or something to find the equation of motion. And hopefully you also learned that the equation of motion always has this form, where we have mass, damping, and stiffness matrices multiplied by the acceleration, velocity, and displacement, respectively. For example, for this little 2 degree of freedom system, the mass matrix is a diagonal matrix with M1 and M2 on the diagonals. The stiffness matrix looks like this, where once you've learned this, it's fairly easy to make sense of. K1 and K2 are the two that connect to X1, so those are the two springs up here that connect to mass 1. Similarly, K2 and K3 are the two that connect to mass 2, and the one that joins them has a negative sign, K2 on the off diagonal. Alright, so the equations of motion will always have this form. And unfortunately, we don't immediately have a solution for these equations. This is a set of coupled second-order differential equations, and you can't just look up in your math book what the solution for this is. And you'll remember that for the single degree of freedom case, we assumed that scalar x was equal to the real part of some constant, complex constant x, e to the I omega t. And that was how we were able to come up with a solution. So we'll do something similar for the multi-degree freedom system, only now we'll assume that the response, which is a 2x1 vector, so we have mass 1 and mass 2, will be equal to the real part of now a constant that's also a 2x1 vector. So we'd have phi1 and phi2, and multiplied by e to the I omega t. We'll assume that both of these masses are moving at the same frequency, so only the amplitude and phase are different between them. Okay, and if you plug that in up above, you eventually come up with this problem which we need to solve. And this is called an eigenvalue problem. Because we're finding for, we have a solution that's homogeneous with the right-hand side equal to 0. So hopefully it's pretty obvious how you would do that. The book goes through this in detail if you didn't see this in your vibration class. But anyway, this is the problem that we need to solve. And in your vibration class, you probably learned how to solve this by hand. So we would take the determinant of this matrix right here, set that equal to 0. That gives us a polynomial called the characteristic equation that gives us the natural frequencies. And then we would plug back in here those natural frequencies to solve for the vectors phi. They're in the null space of that matrix. Those are the eigenvectors or the mode shapes. For the purposes of this class, though, we're going to do everything on the computer in MATLAB. We're not going to bother reviewing any of that because most of the problems we'll be interested in are just easier to solve on the computer, not really solvable by hand. So if we do want to solve this in MATLAB, though, we do need to get rid of any numbers. So if we go back to this example up here, you can do a symbolic solve in MATLAB for eigenvalues, but it's not super useful. So usually we need to make these two matrices numerical. So in this case, we can do that if we let all the k values be equal and call them k, and all the masses have the same mass and call them m. And if we do that, the equation up above becomes this one. 2k, 2k minus k, like that for the stiffness matrix and the mass matrix. And now we can actually factor the numbers out of the matrices. So we divide both sides by k, and that lets us put the k here on this term. And then you can see that we can immediately just pull the m out and put it right here. So now we have this whole problem, and we can write it like this, where we have Kn and Mn. These are just the numerical mass and stiffness matrices. They have nothing but numbers, no units. And then we have lambda that has all of the units in the problem. So if we get it to that point, we can easily plug this into MATLAB and we can get a solution. All right, so let me show you how to do it. And this is the notation that we'll use in MATLAB to solve this. So if we flip over to MATLAB here, I'll just copy and paste from this example that we'll cover later. So what I've done is I've created a mass and stiffness matrix, and then I've told the computer, give me phi and lambda, the mode shape matrix, and the eigenvalues. So notice lambda, as we said over here, lambda that MATLAB gives us will be a matrix, a diagonal matrix that has the eigenvalues on the diagonal. So usually we would need to, we would want to just pull out a vector of frequencies. So what we can do is if we say the natural frequencies are equal to the square root of the diagonal of the lambda matrix, that then gives us just the values on the diagonal and takes the square root. So those are our two natural frequencies. This system would have a natural frequency at 1 radian per second and another one at 1.7 radians per second. And then these are the two mode vectors. So piece of cake to do this in MATLAB. The nice thing is once you know that little trick, you could do that even for a very large system with hundreds or thousands, maybe even millions of degrees of freedom if you have a powerful enough computer. So that's how we get these critical properties of the system, and those properties are the natural frequencies and the eigenvectors. Here I've written them like this to make them a little simpler. Notice these ones, the maximum value is 1, so we would call these unit normalized eigenvectors. And remember, the assumption that we made to start all of this, right, was that the response was some vector times e to the I omega t. So now we would plug back into that. So for the first mode, for example, we'd say that x was equal to phi 1 e to the I omega 1t, right? So so this is the equation that governs the response. Or in other words, each of these eigenvectors is a solution to the differential equation, where we have the masses moving with, in the case of the first eigenvalue, at a frequency of 1, and with a motion where we have x1 equal to 1 e to the I omega t, x2 equal to 1 e to the I omega t. And then the second mode has a different frequency, and in that case x1 and x2 are moving at the same amplitude but with opposite signs. So let me show you this so you can hopefully visualize a little bit. So here we are. Suppose my two hands, oops, make them a little smaller. Suppose my two hands here are the two masses. So the first mode has them both moving in the same direction at one frequency, right? So they have the same sign. So the first mode, we'll just see the masses moving like this. And in the second mode, they're moving at a little higher frequency. And if this one goes positive, this one will go negative. So in the second mode, the two masses will move like this, and they'll move at a little higher frequency. So mode 1 the together mode, mode 2, apart, right? And so they're doing all kinds of little interesting dances, right? All right, so those are the two modes of the system, and they're two fundamental solutions to the system. The modes have an important property, which is that if we take any mode in an n-degree of freedom system, if we take the jth mode and the nth mode, and we take phi transpose m phi, that will equal 0 if n is not equal to j. And, or actually, I guess I should say in the book, like the proof actually says if omega j is not equal to omega n. So we should actually update that. Same down here. But anyway, what this is this is just a dot product. And remember, a dot product given two vectors. If we have vectors A and B, A dot B, the dot product is equal to the magnitudes of the vectors times the cosine of the angle between them. So a dot product is 0 if the angle goes to 90 degrees or the vectors are orthogonal. So this is a key property of modes, and we call it orthogonality. And so these modes form a basis for the solution, or basically anything that the structure does is just a superposition of these modes. And so these are critical to help us understand the motion of multi-degree of freedom systems. And every structure has modes of vibration. This two-mass system has fairly simple modes. We talked about those. But you can take any structure that you can model and you can derive its modes, or in this class we'll learn how to actually measure those modes. So I'll show you a couple examples of that. In my research and as a doctoral student, I looked at this bridge. This was a highway bridge in Switzerland that had also had a train track here. And they had to knock down the bridge to make way for a bigger train. So they did a lot of testing on the bridge before knocking it down, including applying some artificial damage and looking at how that changed the vibration properties of the bridge. But anyway, the thing I wanted to show you here was the different mode shapes that were measured from the bridge. So this is the first bending mode of the bridge. This is just like the mode 1 that we had for the two masses. It's the lowest mode. I mean, it's just like it. It's the same concept, right? Only here we have every point, every node of the bridge has a different degree of freedom, a different mass. And there are all kinds of springs, hundreds of springs connecting all those masses together. But when you solve that eigenvalue problem, you end up with a nice, uniform, simple motion like this. And so this is a fundamental motion of the bridge. It's a key building block to understanding any transient response of that bridge. Similarly, we could look at the second mode. This one is a rocking mode, a side-to-side, a torsion/rocking. And as we get a little higher in frequency, we can see things that are a little bit more complicated now, right? And these are a basis for the response. So if we do anything to the bridge, the motion that we get is a superposition of these modal motions. I'll show you an example of this. This one is going to show an animation where a big block is dropped, I believe right in the center of the bridge. So basically imagine hitting the center of the bridge with a big hammer and watching the vibration. And if you watch it, you'll see these individual modes, these individual ingredients showing up. So you see that? So we get some twisting, so a little bit of that third mode. But then as time advances, we start to see something that looks very much like the first mode. So initially there's all kinds of things going on. Maybe we need lots of modes to describe that. But as time advances, it looks kind of just like a combination of that first mode and third mode. And not very much happening out of plane, right? So those modes make up a basis that let us understand what happens. This is another case study. This is a case where the mass is dropped out here, so we excite out there. And here you see a lot of that third mode excited. You get a lot of motion out here. Oops, that one ended. Let's try that one more time. You get a lot of motion out in this bay, and it does excite some of that twisting coupled to bending in the center section that we saw in the third mode. But a fairly complicated motion. So the moral of the story is any structure, even a real bridge, a complicated bridge, we can think of as just a superposition of some of these relatively simple motions, and each motion has its own frequency of oscillation. And we add all of those up and we can describe complicated motions of the structure. All right, so there's an example. I'll show you one more. That was a bridge. Let's do something totally different, a rocket, how about, right? This is a simplified model of the SLS, so these aren't true modes at all. This was a simple model that one of my grad students made. But here you can get an idea of what the bending modes of a rocket might look like, right? A first mode, a second mode, and torsion modes. And, they have similar properties. They become more and more complicated as you go up in frequency to higher order modes. But, but they do give you an idea of the type of motion that you can get. So, this is, so here's another example. Okay, so that's modes of vibration. What do we do with those? How do those help us solve problems? Well, we'll go through a little derivation that will show that we can use these to make our multi-degree of freedom system into a bunch of single degree of freedom systems. Each mode is basically a single degree of freedom system that governs how the system moves. So to do that, we'll go to the next set of slides. And we're going to do one thing to simplify. Those orthogonality properties said, for example, if we had the first mode transpose times the mass matrix times the first mode, that we'd have some constant, some value, mu1. To simplify things, we're actually going to take the mode vector here, divide by the square root of that constant. So then, if we repeated that calculation with capital Phi1, this would just go to 1. And so we call these mass normalized. Let me show you that quickly in MATLAB. So if we had, let's say we had lowercase phi, as we had a second ago. Okay, so let's say that was the matrix that we got. Phi transpose M phi would give us a diagonal matrix where we have 2 on each of the diagonals, right? And so if we want to correct that, we would say that capital Phi, the first column of capital Phi will be the first column of little phi divided by the square root of 2. Right? Then we could do the second thing for this, or the same thing for the second column. And now capital Phi is mass normalized. Notice that's similar to what MATLAB actually gave us. So if we take phi transpose phi, now we have an identity matrix. So this is mass normalizing. And we can actually do that all in one line of code right here. What this does, this line of code actually does that little mode by mode solution all in one line. And it will give us the mass normalized modes that we want. Okay, so once we've done that, we have improved upon the orthogonality properties that we had. Let's just write them here. The mass normalized mode shape matrix times m times phi again. This one is equal to an identity. And if we were to do the same thing with the stiffness matrix, what we get is a diagonal matrix with the natural frequencies squared on the diagonal, and everything else 0. So that simplifies things down a little bit. And again, that's all we're doing. If we take the simple orthogonality, is we're just dividing through by that number, so that we get a 1 here and 1 times the natural frequency squared here. Okay, so if any of that's unclear, look at the book. It explains a lot of it. This linear algebra might be new to a lot of you. The book goes through a lot of that in great detail, so take a second to read that if this is unclear at all. Once we have this mass normalized mode matrix, this lets us do a transformation, basically a change of variables. We're going to replace the x variables with the mode shape matrix times a new set of variables, eta. Sometimes we use q for those, but we'll match the Ginsburg notation where eta is used. If we plug that into this equation of motion that we started with, this is constant, so if we take x double dot, it's just phi times eta double dot. So anyway, we get this equation, which initially doesn't really seem to have helped us very much. But if we multiply this whole equation by phi transpose, so each of these will have a phi transpose in it. Now you can see that we start to get some simplification, right? Because we just said that this one is an identity matrix. This one is this matrix of natural frequencies squared. So our equation of motion becomes this. And we'll talk more next time, but under some mild assumptions for the damping matrix, it will also be diagonal. And on the diagonal, we'll call the values there 2 zeta omega n to kind of match our standard form. And if we do that, then these equations become completely uncoupled, so we can write them as separate equations. So for the first mode, eta double dot, this constant that we're used to, eta 1 dot, the natural frequency squared, eta 1. For the second mode, the exact same thing, only with the second damping ratio and the second natural frequency. So notice these are completely uncoupled. These are nothing but 1 degree of freedom systems. So we took that multi-degree of freedom system that we didn't know how to solve, and we made it into 1 degree of freedom system. So now we know how to solve it. And we can go ahead and use any of the things that we learned in the previous lecture to solve it. So for example, in the general damped case for an arbitrary mode, the solution is just some constant e to the lambda t, where lambda, remember the definition from last time, we have the damping ratio and the frequency of that mode, and then the damped natural frequency in the imaginary part of that mode. So given any system, we could come up with eta 1, eta 2, and so on. And then if we go back to our assumption, our coordinate change, that will tell us how to get back the physical response. So this is really powerful. The one thing we haven't talked about that we will need to do this is recall that this depends on the initial conditions of the system. And probably any initial conditions that we're given are going to be on x, right? We might know x at time 0. We might know x dot at time 0. So we'll need to figure out the initial etas from those. And it turns out we can do that really easily just by inverting this equation right here. So eta is just phi inverse times x. Phi is an orthogonal matrix, so it's invertible. So if we knew x at time 0, we could easily plug in here to get eta at time 0. And similarly, if we knew x dot at time 0, we could get eta dot at time 0. And then we'll be ready to go, because if we know eta of 0 and eta dot of 0, that will let us get that constant AR. Remember, that's a complex number, and it depends on the initial displacement and on the initial velocity of the system. So once we have that, we have everything we need to solve the problem. All right. I will mention also, because of these orthogonality properties, we don't have to actually compute phi inverse. If phi transpose, let me write that a little nicer. If phi transpose m phi is equal to an identity, well, we also know that phi inverse phi would be an identity. So by inspection, this has to be the inverse of phi. So we can actually avoid calculating the inverse and just use phi transpose m to get that. So, so we can use this to solve the problem. And I'll show you quickly in this code where that's done. So I define, let's see here, I actually used x rather than q, or q rather than x, sorry about that, matching the Ginsburg notation. But if we have these initial conditions, then my initial conditions on eta are phi transpose m times the initial displacement for eta dot phi transpose m times the velocity. So if I run this whole script, let it run for just a second. So what I would get, eta 0, so remember we had q0, q dot 0. So eta 0 ends up being negative 1.4 and 0, negative square root of 2 and 0. So this particular initial condition ends up exciting only one of the modes. And if the velocities are 0, then the initial etas are 0. So those will all be 0. And I use that to define the two constants. So n1 and n2 are the two, the AR constants that I had in those other notes. So those are those same constants. And then I was able to say that eta 1 as a function of time is just the real part of that constant, e to the lambda t. And eta 2 is the real part of that constant, e to the lambda t. So I have the whole solution ready. So these figures kind of show you everything. So this one shows you mode 1 and mode 2. So mode 1 is basically a single degree of freedom system, transient response. Mode 2 ends up being 0 in this example. And then if I transfer back to physical coordinates, remember all I have to do that is just use this equation right here. Physical coordinates are the mode shape matrix times the eta. So in this case I have an eta 1 of t and a 0. I can transfer back and this is what I get. And notice here that what I'm getting is the two are right exactly on top of each other. So mode 1 and mode 2, oops, there's extra lines there so it's hard to see. But anyway, x1 and x2 are moving together. That's the two masses moving in sync. So that's perfectly a motion of mode 1 only. We could get, if we took a more general case, let's try this one right here. If we took a more general case, we'll get both modes being excited. Okay, so now in this case, we see mode 1 and mode 2, both are excited. If you zoom in, mode 1 is a lower frequency oscillation with a different initial amplitude. Mode 2 is higher frequency. When we put those together, though, and we go back and look at what happens to mass 1 and mass 2, now we have a pretty complicated motion. Mass 1 and mass 2, moving in and out of phase, and sometimes one's moving one way, the other's moving a different way. But anyway, this complicated motion can be understood as a superposition of two 1 degree of freedom systems. So that's the key to modal analysis and the key idea here to all of this. So I hope that helps and that made sense. If not, you really want to spend some time with this derivation. This page right here, this derivation is one of the most fundamental things in vibrations and that we'll need in this class. This idea that we can uncouple equations and we can describe responses as superpositions of modes. So I encourage you to, take an arbitrary system, go through, write out that derivation, do the whole thing by hand, make sure that every step makes sense to you, and that you could basically do that derivation in your sleep. Once you do that, you'll be well on your way to understanding some pretty complicated vibration problems.